How is everybody? Are you still tired? Thanks, John. So I'm going to do how to talk to hardware, JavaScript firmware in 30 minutes, which is a tall order. So please forgive me if I speed through some concept or if I abbreviate. Like, I won't go over all of how you do firmware in JavaScript in 30 minutes. This is actually kind of a hard concept for a lot of people, including experienced engineers. So if there's anything in here that just completely flies by, that I say really fast, or that you haven't been introduced to before, I won't probably have time for Q&A here. But please approach me afterwards if there's something you want to learn more about. I would be delighted to fill in the gaps on what I didn't have time for in here. So I'm Kelsey. As CJ mentioned, I'm one of the creators of this thing called the Tessel, which you can basically think of as a Node API for the physical world. And today we're going to solve a problem. And the problem that we're going to solve is I want my project to be able to tell me whether it is oriented right side up or if I flip it over and it's right side down. And I lost all my probes. Don't worry about that. So today's talk is not about Tessel. It includes a Tessel for the sake of convenience because I want to write my firmware in JavaScript. But this is what it looks like to solve my problem with Tessel. I've got 2 node requires. I say that I'm going to use this Tessel thing. I'm going to plug in this accelerometer module on port A. And when it gives me data, I'm going to print it out. And because acceleration, as you all know, is a constant downward, or because gravity is a constant downward acceleration, I'll get a different z-axis sign, negative versus positive, if I'm like this versus like that. We're like 1 minute into my talk, so that's why I'm not telling you about Tessel today. Because it's much more interesting if we take a look further in and don't use the APIs that we've already written. So what I'm going to do is show you the basics of how we go from a piece of hardware like this, with this little black chip on it, the MMA84 accelerometer, how we look at the data sheet and interpret the signals and talk to it in order to get useful information. So if you look at the full stack, which is not in this case a mean stack, we're going to talk today basically from signals on a wire to zeros and ones, binary and hex numbers, and go all the way out to printing information in English. And if any of you are able to come to the workshop tomorrow, I think it might be full, but essentially pay attention because we're going to make you do this tomorrow. So jumping right in, how talking to hardware works. There are many ways that a signal can play on a wire. You've got your analog, you've got your pulse width modulation. Today we're only going to talk about digital signals. And the reason for that is a microcontroller will typically use just a digital signal. It's very simple. It's either on or it's off, right? And this is the microcontroller chip on here. And that's what it speaks, is ones and zeros. So we need to figure out how to use ones and zeros to convey more information than just on and off. Because we only have that very simple information, we have to add the third dimension of time, right? And you all are probably familiar with Morse code. What we use is communication protocols. So we toggle ones and zeros with specific timing on specific wires in encodings that create messages that are more complex. So for example, over here in this diagram, this is using a protocol called SPI, which we aren't going to use for this accelerometer. But it's got 4 different wires, clock, one that talks from the master device to the slave device. I apologize for the terminology, it's like ingrained in here. But it means that this device has complete control and this device has no control. And so we've got one where the master device talks to the slave, and one where the slave device responds to the master, and this other line, which I won't go into right now. Different protocols use different numbers of wires and different specific encodings. So let's try one. So this is a different one. This is called UART, also known as serial. And what we're going to do is we're going to send the words hello world over the wire here. Hold on. I lost all my probes when I picked this up, so you get to watch me painfully attach this. RX and TX. So serial is a protocol that uses 2 wires, and the third wire is just ground, which you need in everything. So, by the way, the device that I'm hooking in is called a logic analyzer, and this is a really nice one. It's by this company called Salier. And what a logic analyzer does is it lets you have a look specifically at what the signals are saying on the pins. So you actually get to watch and record the messages that it's sending. And it even does stuff like interpret it, and I'll show you in a second. I think that's plugged in properly. Come on. Sorry, hardware on stage is like this at the best of times. There we go. All right. So what I'm going to do, essentially, what we're taking is a message, and we're sending it from the Tessel and communicating it outward. And in this case, I don't even have a microchip attached to it, so it's not communicating with anything except for this logic analyzer here. And the important bit is what I'm showing here is this is the JavaScript code I'm going to send. And this stuff over here is settings in the logic analyzer, which is over here, which tell it how to interpret it. And the important part is that they match, right? So here we've got data bits, 8, baud rate. This is the speed at which it's sent. And you can see that we've got the same baud rate, the 8 bits, et cetera. If we had more time, I'd tell you what those mean, but it honestly doesn't matter very much in this context. So what I'm going to do is run this code. And at the same time, I'm going to capture it. And so this is going to wait for something to happen over on the Tessel. And I've set it so that when channel 3, which is this orange wire, goes high, it'll start collecting samples. So it's found my Tessel, and it's writing, and it's running, and uh-oh, something's not connected. Oops. That's what you get. I plugged it in backwards. I'll try that again. Right. Connected. Writing, running, waiting for trigger. And it took samples. Perfect. So I can pause it early. And so what you can see here is we've got this async serial line. Something happened to start it, so that was the initialization of the code when I required Tessel. And if we zoom way in, we can see that some up and down motion happened, and that's the 1s and 0s. And if you zoom even further in, you probably can't read this very well because this program doesn't let you change font sizes, but it says, "Hello world." And I will take a screenshot and let you see in bigger. Yeah. So that's pretty cool, right? Now we've seen how you can take 1s and 0s and really obscure-looking bits like this and over a wire talk to something. Getting back to our problem solving. So we want to determine whether this is upside down or right side up, right? So I mentioned this earlier very briefly, but the easiest thing to do to determine right side up and upside down is to find gravity. One of the fun bits about working with hardware is that you get to choose your different sensors, right? So you could do this in a bunch of different ways. You could have some kind of electronic level, or you could have some like magnetic switch that teaches it what's upside down, right side up. You could have a light sensor that gets covered if it gets flipped over. But what I've decided is the most reliable, and what your smartphone manufacturers have also decided is the right answer is an accelerometer, because you can very consistently get the direction of gravity, right? So in your smartphone, it's the thing that lets your phone know whether it's portrait or landscape. It's just an accelerometer finding gravity. So we're going to do that, use an accelerometer, and because I want to use JavaScript, and because maybe in the future I want my project to have internet connectivity, I'm going to write on a Tessel too. So how do I actually do that? So I've taken this thing here. So this is my accelerometer module, which is Tessel's. But what I'm actually going to try and talk to is this little black chip. And if you look really close on it, in tiny, tiny font, which you definitely can't read, it says MMA84, which is its part number. And this whole red board is what's called a breakout board. And it just makes it easier for it to get plugged in. And it's got a couple of resistors and capacitors so that it can handle charge, so it can have the right address, which we'll talk to in a bit. So what we're looking at is that little black bit. And as you can see here, it looks like this. And it has this data sheet. It's pretty cool. Hardware bits come with manuals in the general case. What's sort of unfortunate, and also nice, is that it's a 54-page document that you have to look through. And the thing is, you actually have to read the whole thing. If you're going to do this stuff, it's a really good idea to actually read the entire data sheet. I won't make you read the entire thing, but I'll show it to you here. And we're going to reference it during this talk. There's a bunch of different stuff in here. It talks about, here's what each of the different pins do. It's got a table of contents. It tells you exactly how it's going to work. Talking about Earth gravity, which we've talked about ourselves. Basically, everything you could possibly want to know about this part is supposed to be in this document. So the first thing you want to figure out is, how does this talk to this? And this is looking for our communication protocol. So we already saw serial, we saw SPI. This one has I2C. And how do I know that? Because it says so in the table of contents. So I know that I need I2C. Then I need to talk from the JavaScript side. So I go to tessel.io/docs, and it redirects over here. I look in Hardware API and find I2C, right? So we need to be able to specify from both directions. So that, remember when we had the baud rate, what is that all about? Remember when we had the baud rate of 115/200 and the 8 data bits and all that sort of stuff? We need the same sort of stuff for I2C, but a little different because it's a different protocol. So in the case of I2C, each hardware thing will have a built-in address. And in this case, the address is, in this case, the address for the accelerometer, which you can find in the data sheet, but I won't dig through it for the sake of your time, is 0x1d. So we're then going to initialize I2C is a new I2C port on port A. And we're going to do the very first thing that you typically will do is that there should be a who am I. So this is a thing that lets you say, well, I've hooked it up correctly and my software communication is set to the appropriate levels, right? So I've just plugged in the accelerometer on port A. And I'm going to need to move this over to read on the I2C lines, which are SCL and SDA. One of them is clock and the other one is data. Make a really confused face if you're lost. Okay, you all seem either fine or asleep. Okay, cool. So I'm going to do the hello world for this particular part, which is not writing the words hello world onto it, but actually looking for this thing called who am I, which you can find in the data sheet. One of the most useful bits of the data sheet is this thing called register descriptions. And it tells me if I want to get different kinds of data, like status or out X or out Z, or who am I, it says that the address of the register that has that information is here at 0x0d, and it should return information. And in this case, it'll always just return 0x2a. That's just what this particular device says. So I'm going to ask it to tell me, oops. I'm going to ask it to tell me what is at that 0x0d, and we expect the answer to be 0x2a. So it's connected, it's running, it's looking for a trigger, and it's sampling. Cool. So let's go find it. Here we are. Some things happened. And this one says 0x2a. Cool. And it says 2a over here as well, because I told it to. Excellent. So we know that our accelerometer is hooked up correctly. Sorry, let's get this back. So we know our accelerometer is hooked up correctly, and we're able to talk to it. So that was the first time that the Tessel here has talked to this little MMA84 device on here, and this talked back to it. So communication's working. So back to the problem. We know that we only need the z-axis, and this little image on the side here is from the data sheet, and it says that if it's upside down, you'll get a negative z, and if it's right side up, you'll get a positive z. So how do we learn whether the z is negative or positive? Well, we're going to look. These are copied and pasted from the data sheet. So this is the out z. There's two of them that say out z, and there's MSB and LSB, and that stands for most significant and least significant bits. Maybe those of you with classical computer science education already know these things, but most significant bits are going to be like if you had 100, or if you had 123, the most significant part of that would be the 100, and the least significant would be the 3, right? So since we only care about the negative versus positive, we'll expect this to be in the most significant digit. And specifically, there's this thing called 2's complement, which according to the data sheet is what this device, what this MMA84 accelerometer device uses. And 2's complement, which I'm going to grossly simplify right here, is a way to say negative versus positive by using the most significant bit as a placeholder for a negative or positive, or a negative or positive sign, right? So if it's a 1, there is a minus sign present, and if it's a 0, there's no minus sign present. There's more to 2's complement, but that's the important bit for this demo. So in this case, the most significant bit is bit 7, and if bit 7 gives us back a 0, then it is positive, and if bit 7 is a 1, then we have a negative number. Okay, so let's start with, we need to read out z MSB. So if we look back at the registers here, this one, it says out z, the most significant bits are located at 0x05. So far, so good. We've got the same stuff up here. Now we're looking at different register to read. We only need the one register. And within an interval of 1 second, we're going to ask it for that register, okay? And usually, I'd like to do a demo here that shows you the importance of reading the data sheet. If I ran this as it is, I would get this repeating value over here of 94, no matter how I move this around, whether I flip it upside down or not. And that is because I didn't read the part where it says, oh, the system is in a low power mode when you turn it on, so you actually have to tell it to start reading data for it to start reading data. Read the data sheet, that's the moral. We'll skip to it. And all you have to do there is you get this diagram that says, go to the control register and set the active bit to 1, of course. And so you go Google around or you search around in the data sheet and you find this thing called the control register and set the active bit to 1. So let's go ahead and do that. So we've got the same stuff we had before, right? That active interval, address to read. But before that, we're going to do this set active where we send the buffer that says, of these 8 bits, set the last one to be 1. Great. Does that look good? You look good? Great. 06 pull. So what we're expecting right now, and I'll take these off, we don't need them anymore. What we're expecting right now is that if I take this device and I have it one way, and then I move it another way, we're going to get different data coming out. Oh, and if we go back to the console here, you can see that in fact data looks different. If I've got it upside, or if I've got it right side up, it looks pretty similar over here. If I flip it over, something different is happening. So that's good. What is that? What is that number? So the system's awake. We're getting data. What we haven't done is interpreted the 8 bits that we get back for just this first bit. What we're seeing right now is the number created if you interpret the top 8 most significant bits as a number, which turns into a hex value, which is the same as a, yeah, don't worry about it. What we need to do is isolate whether or not this first bit is a 0 or a 1. And we're going to do some sort of weird trick here, where we need to find out if the number that we get back is bigger than 0, 1, 1, 1, 1, 1, 1, 1, because anything bigger than that is going to have a 1 in the most significant digit. Yeah, ask me about this later if it's confusing to you. This was like a weird mental trick for me. But basically that's isolating whether this is a 0 or a 1. And so we'll be able to print out if it is a 1 here, then we know it's negative, and if it's a 0 here, we know it's positive. So T2 run 07. And I'd like to encourage you again, if I think I might actually have time to take questions at the end here, which is great. So please, if I have confused you here, please raise your hand and let me know. So we're getting a result, and this says positive, right side up. And yeah. Cool. So it works. And I'm hoping that last bit wasn't terribly mystifying. But we've got basically the problem solved here of we want to tell whether it's right side up or upside down without using a built-in API. So that's just the very start of it, right? So what I've done with this is the Excel MMA 84 module on Node. It's got more functions than this. You can tell it how fast you want to do it. You can take all these different register descriptions and break them out into the JavaScript software. They're all like part of the Node API. There's just endless stuff that you can do once you've gotten your basic information out of it. But that's all I'm going to do up here on stage. And I hope if you want to come to the workshop tomorrow, I hope you can come up with some interesting interpretations. We've got sensors that aren't on pretty breakout boards like this, so you can learn how to do alcohol sensing and load force and all this type of stuff that we actually don't have any Node modules for, so you'll be inventing it. That's all my demo. If you'd like to look at these slides, I actually have a few other demos that I didn't show today. I showed these ones. And if you want to look at a slower step through, these other ones are available to you. And you can find my slides if you go to GitHub, Freehole, Singapore demos. Oh, and I have a book that's recently out, if you'd like to get into it. It's not just Tessel, it's all sorts of different boards. Does anybody have questions? There's no way I explained it that well. Yeah? Oh, do we have a microphone? Thomas,
so,
right here.
Over here.
So maybe for the last part, when you compare it's upside down, it's up or down, you can just shift the bits 7 digit. Just check the most significant bit. It's mentally I feel it's easier to understand that than comparing with a weird binary number. You understand what I mean?
Yeah, you're right. So it depends on what kind of mental aerobics are easier for you. He was suggesting that instead of comparing this 0, 1, 1, 1, 1, 1 number, I could just shift the bits down in order to just get rid of these extra numbers that I don't care about. Yeah, for me this was easier. For you it might be easier to do it a different way. And that's kind of what's fun is if you start with looking up sensors online, you have just a ton of freedom to mess around and decide what implementation you would like.
We have a bit more time if you have another pressing question. You left everybody speechless.
Well, all right then. I'll expect all of you to make me a firmware thing tomorrow.
Go and meet Kelsey afterwards, right? And maybe take a look at the hardware yourself too.
All right. Give a round of applause to Kelsey.